Alright, in this video we're going to take a look at exact ratios for the 6 trig ratios for 45, 45, 90 triangles. And we'll take a look at 30, 60, 90 triangles in the next video. So 45, 45, 90 triangles are also known as isosceles right triangles, and they can be created by drawing a diagonal across a square. So bear in mind a couple things from geometry, that a square has 4 equal or congruent sides, and that the angles are all 90 degrees. Also, when you draw a diagonal through a square, it's going to bisect or cut that 90-degree angle in half. So this is 45 here, 45 here, and these two bottom left angles are also going to be 45 degrees. So if we look at this triangle here, for instance, we have an isosceles right triangle or a 45, 45, 90 triangle. Since the sides of the square are the same length, we can use whatever length we want. So for simplicity, we're going to use a length of 1, and the diagonal can be found using Pythagorean theorem. So we can use a length of 1. We can actually use any length we want, and it'll scale all proportionally. But 1's the simplest side length to use. So if we have a base and a height of 1, then we can use Pythagorean theorem, a squared plus b squared is c squared, to find the length of the diagonal. So in that case, 1 squared plus 1 squared is 2. The square root of 2 is just square root of 2. So our hypotenuse in a 45, 45, 90 triangle is 2, square root of 2, pardon me. And each of the other sides, the base and the height, are each a length of 1. So example 3, we're going to find the exact values of the 6 trig ratios for 45 degrees. Again, we have opposite is 1, hypotenuse is square root of 2, and adjacent is 1. So first up, the sine of 45 degrees, we have 1 opposite over square root of 2 hypotenuse. And because we have a square root of 2 in our denominator, we have to rationalize it by multiplying the top and bottom by the square root of 2. And when we do that, across the numerator, we get 1 times the square root of 2 is square root of 2. And the denominator, square root of 2 times square root of 2, is square root of 4, which is 2. So no more square roots in denominators. Yay. Cosine of 45 degrees, also 1 over the square root of 2 for adjacent over hypotenuse, which we just saw rationalized to square root of 2 over 2. So sine and cosine of 45 degrees are both square root of 2 over 2. Also, the equivalent of 45 degrees in radians, pi over 4. The sine of pi over 4 and the cosine of pi over 4 also square root of 2 over 2. So if we replace a degree with its radian equivalent, we're not going to change our trig ratio at all. Tangent of 45 degrees, opposite 1 over adjacent 1, and 1 over 1 is 1. So tangent of 45 degrees is 1. So those are the big three, and we're going to take their reciprocals for cosecant, secant, and cotangent. So cosecant of 45 degrees, hypotenuse over opposite, square root of 2 over 1 is just square root of 2. Secant of 45 degrees, hypotenuse over adjacent, we have square root of 2 over 1, and that again is square root of 2. So just like sine and cosine of 45 degrees are the same, secant and cosecant of 45 degrees are the same. And then finally, cotangent, adjacent 1 over opposite 1, it simplifies to 1. So those are the 6 trig ratios for 45 degrees. In the next video, we're going to take a look at 30, 60, 90 triangles. Both 45, 45, 90 triangles and 30, 60, 90 triangles are going to be very important in the next section on trig functions of any angle. But I'll see you in the next video for 30, 60, 90 triangles.